All right, so we didn't get to direction angle. Anybody figure that out on their own? Yes? Skipped it? Okay. It's okay if you skipped it, no worries. We need to know it though, so tack it on. If you didn't do that on your homework, for your sake, I would go back, although it is really not a big deal. There is a way people miss this consistently on every test, but it's more of they just forgot. But let me just show you what I'm talking about. So for a direction angle, let's just say I gave you this vector, -2, 7. Now you know that -2, 7 would mean that I move 2 to the left and then 7 up, and I draw a vector, right? And I could technically start anywhere I want. So I could have 2, 7 here, 2, 7 here, 2, 7 down here. Directions, vectors just show magnitude and direction, not initial and terminal location necessarily, right? So this, I don't know where it's starting, but if I'm going to draw a picture of it, why not start at the origin? So if I was drawing a picture of this, and I knew that I was going to go, say, left 2, and then up 7, that would put the beginning and ending right here. And again, I don't have to go in this direction. I don't have to start here. I'm just choosing to start there. Are you with me? So that's my vector. Now the direction angle means what is the angle measured from 0 degrees? So it would be whatever that is. That would be my direction angle of that vector. Now how am I going to calculate that? Well, it just goes back to trig. So I've got a triangle here, right? And if I think about this triangle, it's not a special triangle, but it is a right triangle. And I have that side -2 and that side 7. So if I needed to know this angle, what trig could I use if I know those two sides? Which would be the op. Now I know if you're looking at this, you're like, wait a minute, is that the angle or is this the angle? Well, that angle looks acute. I don't want the acute angle. The acute angle is what we have if I drew this triangle, 2 and 7, and found that theta. But I can actually find this angle by thinking of it just like this, but just including the negative in there. And it'll do it for me, sort of. You're going to catch one little thing. So right here, what trig function uses opposite and adjacent? The tangent. So if I want to say tangent of theta would be the opposite over the adjacent, I could do that, right? And I could go in there and look at the tangent curve and find all the places that tangent are between 90 and 180 degrees. Now that's probably not what you would do. What would you do to find that angle right now? Plug what in my calculator? Are you going to graph it? Or are you going to do inverse tan? Okay, that's where you get in trouble. It's just a small bit of trouble. You just got to think for a second. Right here, if I do the inverse tan, which is what I'm going to do, and I type this in my calculator, inverse tan can't give me that answer. And why is that? Because inverse tan is defined where? From -90 to 90. So guess what it's going to spit out? It's not going to spit out that one. It's actually going to spit out the other place that tangent is negative, which is where? That one. Now that's okay, because if it spits out this one, what do you think the difference is between these two angles? 180 degrees. So look, I'm going to go to my calculator. I'm just going to type that in. So make sure that you're in degrees if you want it to spit out degrees. So I'm going to go check I'm in degrees. So inverse tan, trig, inverse tangent, the fraction 7 over -2, and it gives me -74 I'll just call it 0.1. So it gives me -74.1. Well guys, you already know that anytime I move left, if I move left, there's no way I'm going to be in the first or the fourth quadrant, am I? So if you ever look up here and you see, wait a minute, I'm moving left first, that puts me in the second and the third. Inverse tan can't give me an answer there. Well then all you have to do is say, well, whatever my calculator gives me, I'm just going to add 180 degrees to it. And when I add 180 to that, I get 105.9, and that looks more like this thing. But if it was a positive movement, like right here, this is 4 to the right. Well, if I move 4 to the right, I'm guaranteed to be in either of which two quadrants? First or fourth, and I'm fine there with inverse tangent, aren't I? So on something like this, and remember, don't be bothered by that. That's the same thing as me giving you what in component form? 4 negative 6. So again, for the angle, all I got to do is do inverse tangent, y over x, right? Y over x. But in this case, I don't have to add the 180 because my calculator is going to give me an answer that makes sense. This picture right here, if I were to graph it, I'd be over 4 down 6. I would be pointed in that fourth quadrant where your inverse tangent is defined. Totally fine. So on that second one, I'm just going to have inverse tangent of 4 over, what do we have, 6? No, 6 over 4. Over negative 4. So negative 56.3. I'm great with that. That is definitely in between negative 90 and 90. It is definitely that angle right there. I'm good. So I don't think most people don't have any issue with remembering inverse tangent of y over x, inverse tangent of y over x to find the angle. The thing people forget is the plus 180, when to do it. And when do you do it? Whenever I'm going to be in the second or the third quadrant, which basically boils down to whenever your x coordinate or your movement left or right, your I value or whatever, whenever that's negative and you're outside where inverse tangent would spit out an answer, then you're going to have to go and add 180. Now, if it's a unit circle value, what if I gave you something like this? Well, in that case, do you really even need trig? I mean, do you need to pull out inverse tangent, or could you say, hey, when do I go over a little and down a lot? What angle is that? 240, right? So I know the angle right now. I can say, oh, the direction angle of that vector is 240 because it's a unit circle value. And I don't need to add 180 to that, do I? I already know it's in the right spot. Are you with me? So if I can use a unit circle, use it. But if it's something that I don't recognize like this, then make sure that you use the inverse tangent, y over x, and add a 180 if it's in the second or third. And how can you quickly tell if it's going to be in the second or third? If the initial component, that x component, if it's negative. All right, so that's it for direction angle. So what you should know, right, does anybody have any questions? Yeah?
I know what to use, like, would like 330 and negative 30 be like the same answer? Or just different?
Yes. Yeah, I don't care. Yeah, the only reason I cared before is because, and I honestly didn't care, like if I gave you a problem that said, if I gave you a problem that said solve sine of theta equals negative 1/2, I did not care if you said, hey, theta equals negative 30 plus 360n, or if you said theta equals positive 330 plus 360n. It's the same thing, right? Because if I take that and subtract the 360, there's my negative 30. If I take that and add 360, so I didn't care which one you used. I only cared whether you wrote negative 30 or 330 if it was like an inverse tan problem. Like if it's an inverse tan problem, like if the problem, or say inverse sine. Say the problem was inverse sine of negative 1/2. Well, in that case, you can't use 330 because 330 is not in the inverse sine range, is it? Inverse sine has to be between negative 90 and 90. So that would force me to just use negative 30. But if I'm not dealing with inverse sines here, am I? I'm dealing with a tangent problem. On this, you can, now I convert it into an inverse tan, but you're fine. If you want to write negative 56.3, that's the location. Right? If you want to add a direction angle that's positive and call it 303.7, that's fine with me. Are you with me on that? Because really, I didn't tell you what to begin with. You could have begun with that. You could have begun with that. It's all about location that matters, not some trig rule. So you really kind of like lessen up the restrictions in something like this. Y'all track with me? Okay, if you can go through all of these if you can answer all these questions, that I'm about to ask you, which by the way are all good test questions, then you're in a good place right now. If you're not, put a star by the ones you don't know and make sure you go back and review those. So first thing, oh, we didn't talk about this, the zero vector. Okay, a zero vector is kind of an odd vector, but it's going to come into play very soon today. The zero vector is a vector that moves 0 to the left, right, 0 up or down. And if it was 3 dimensions, it would have 3 zeros. It's not much of a vector though, right? Here, I'm going to push you with the zero vector. I mean, it's doing nothing, right? I'm not pushing this way, I'm not pushing this way. It is kind of an odd vector, but I could say that there is a zero vector wind blowing right now. Well, okay, it's blowing in, I don't even know what direction, right? It's kind of odd because I can't find the direction angle. What's inverse tangent of 0 over 0? Bizarre, I can't divide 0 by 0, right? So it's a weird little vector, but it does come into play in vectors. All right, so I just want you to hold on to that for a second. And then standard position of a vector, and then I'm going to sum it all up. Standard position of a vector just means like if I want to start you at the origin, kind of like, you know, starting at 0 degrees, but starting at 0, 0 on the origin when I sketch it, that would be standard position. I don't know that that's going to show up again, really. But if I did want to draw a vector, I can technically put a vector anywhere based on its movements. But if I want to start it at kind of the origin and talk about it from there, that would be what this is talking about. Okay, now let's sum it up. So if I gave you, and I asked you to find a vector that had that initial point and that terminal point, how would you find it based on what we learned yesterday? How do we find vector V? Loud and proud. What? I want to find the actual vector, not the magnitude. These are points, right? But notice they don't have brackets. So how do I find the vector? So take the final or the terminal point and subtract the initial. So I want to go terminal -4 minus the initial x-coordinate, 5. And then I want to take terminal -13 minus the initial -2. And minusing a negative does what? Adds. So I end up with -9 and -11. So that would be the vector from this initial to that terminal. But again, to do that, you always go terminal minus initial. That's in your notes if you forget that. And if it happened to have three components, like if the points were x, y, z, you just do the same thing again with the z. Find the magnitude and the direction angle of that vector. Okay, how would you find the magnitude of v? And again, if you don't know this, you need to star this. Okay, that's where you do the square root, right? Because if I go over 7 and down 4, I can find the length of the vector by just doing Pythagorean theorem. So basically the square root of the 7 squared plus the -4 squared, which is whatever 49 and 16 root 65. And you can leave it exact, or if it was a calculator problem, you could type it in your calculator and get 8.1 or whatever that is. But root 65 is great with me. And then the direction angle of that, how would you find the direction angle based on what we just learned? So the angle would be inverse tan of y over x, so -4 over 7. And am I going to have to add 180 to that? Why not? Because it is in the over and then down. I'm in the first or the fourth. In this case, the fourth. So do you know what kind of what kind of value I'm going to end up getting? Or what kind of angle I'm going to end up getting here? It's definitely going to be a negative angle because it's down there in the fourth quadrant. So -29.74, I'll just call it 0.7. But just round to whatever it tells you to round. And I don't need to add 360 to that to make it positive. That's totally fine. Okay? And then I'm going to scroll up here for number 3. Find the magnitude and the direction of that vector. Erase all of that. So how would I find the magnitude of that thing? Actually, it's vector W. So what do I do? What do I square root? That's right, the -3 and the -6. I don't square the I and the J. No, because the I and the J are just telling me what? X and Y movement. It's just a notation to let you know, oh, I'm moving this way or I'm moving this way. X left and right, J up and down. So don't square the I and the J. That's not an imaginary I. So just square the -3, square the -6, add them together. So make sure you're careful about that. That gives you 36 and a 9, which would be a √45. So either type that in your calculator to get a decimal, or at least rewrite it as 3√5. And then how do I find the direction angle of this? Inverse tangent of y over x, which would be -6 over -3, which is technically +2. But what do I have to do on this one? Add a 180. And why do I have to do that? Yeah, because it's clear that I headed left first, which is going to place me either in the second or the third, in this case the third, and inverse tangent cannot give me an answer there. So what this calculator thinks, when you type that in, the two negatives cancel and it sees plus over plus, that would be in the first quadrant. But it's not in the first quadrant, it's in the third quadrant. But it's always going to be 180 degrees away. So I'm just going to say, oh, negative right there, don't forget to add a 180. And if you didn't have a calculator on your test and I asked you this question, since I don't know what inverse tan of 2 is, I would just leave it like that. All right, there's nothing wrong with that. You might not have a test. So you might not have a calculator on this test. I haven't decided yet. So anyway, what I would end up with here is a 243.4 degrees. So your calculator would have spit out 63.4, and then you just add a 180 to it. All right, component form. Now component form is like the brackets with the two components, right? How do I get those two components if I have the angle and the magnitude? We talked about this yesterday. Who remembers? If you don't know it, put a star by it. Yeah.
Do 4 times the cosine of 120.
To find the x, right? So remember, normally x movement, I look at my unit circle, and what do I look at? I think about the cosine value. Or if I want the cosine of the angle, I think about the x value. That's not changing. X is still linked to cosine of the 120. The only difference is, now it's not a 1 unit length, it's a 4 unit length. So multiply by 4. And then the y is what? It's still linked to the sine of the angle, right? Except again, it's sine times that 4. And then you got to know your trig functions, right? What's cosine of 120? -1/2. And what's sine of 120? So when I do the math on that, I get y equals 2√3, x equals -2, or whatever. X is -2, y equals 2√3. Write it in component form. And if you wrote it with I and J, you'd get credit for part of it, but you'd miss the part that I think is worth knowing. Like, I need you to know that component form is that, and that unit vector form is something else. All right, what about number 5? It says find the sum of the vectors. And how do you add vectors if they're components? We did that at the end of the day yesterday. How do you add them? Add the x's, add the y's, new vector. And if you have it written in IJ form, add the i's, add the j's, right? So that's how you add them, but I don't have them in that form. So what do I do if they're not in that form? Anybody? Put them in that form. So if I have that vector and that angle, how do I find vector v? Magnitude cosine of the angle, magnitude sine of the angle, sorry, angle's 30. And then use your trig to simplify, use your trig to simplify. And then go to W. What's W? Magnitude cosine of the angle, magnitude sine of the angle. And then use your trig to simplify. And hopefully you know those unit circle values enough to where you can actually get through these without really getting bogged down. And now, how do I add the two vectors? Add the x's and add the y's. Now, these aren't pretty x's. What's 5 root 3 plus 5 root 2? Well, 5 root 3 plus 5 root 2. I can't simplify that. What's 5 plus 5 root 2? Well, I don't have like terms. I can't simplify that either. But I could write the sum of the two vectors that way. Don't get creative and call this 10 plus root 5 or something like that, right? Now, find the unit vector. Now, the unit vector I haven't talked about either. The unit vector is not the same thing as unit vector form. Okay, now what is a unit circle? It's a circle that what? The radius is 1. So what do you think a unit vector is? A vector with the radius or a length of a magnitude of 1. Okay? Is that magnitude 1 right now? What is it? What is the magnitude of this? Root 29, because it's the square root of the 4 and the 25. So if the length of this is like 5.5, how do I make it go in the same direction as that? How do I shrink it down? Now, we said yesterday that when you multiply by a scalar number, you change the length of the vector, but not the direction, unless it's a negative and when you reverse direction. So if I don't want to change the direction, could I multiply this vector by something or divide it by something to shrink it down to a length of 1? Now, what do you know about numbers? If I divide them by themselves, what do I get? 1. So what if I took this vector and divided it by that magnitude? Or multiplied by the reciprocal of that magnitude. Check it out. We know that this vector has a magnitude of root 29. I want it to have a magnitude of 1. A unit vector has a magnitude of 1. So I'm going to take this vector and I'm just going to divide it by its magnitude. And that becomes the unit vector in the direction of v. So check it out. I'm going to take -2, 5, and I'm going to basically divide each component by root 29. And that gives me -2 root 29 over 29, comma, 5 root 29 over 29. And there are probably very few things in this world that you would look at and think, oh yeah, that has a length of 1. But if you did the magnitude of this now, check it out. The magnitude of this new vector, I'll call it unit vector v. I would take the what? To find the magnitude of this thing, what would you do? Square that. 4 times 29 over 29 squared. You tracking with me? Plus 25 times a 29 over a 29 squared. I'm going to do some creative math here so I don't have to multiply 29 squared together. Even though it's 849 maybe?
Yes.
841? 841 I think? But anyway, right here, check it out. If I take 4 times 29 and add 25 times 29 and put it over 29 squared, couldn't I creatively factor out a 29 or cancel a 29 out of all of these? And then what do I end up with?
Wow.
29 over 29, which is 1, square root of 1 is 1. So I proved it. My vector actually is a unit vector. But the actual unit vector is just this. Okay? It's just that thing. So for you, add that to your list. And by the way, it's in your formula sheet I gave you. To find a unit vector, just take a vector and divide it by its magnitude. And you will shrink it down to a length of 1. And in physics, a lot of times when you're finding forces or friction on a normal plane, what you have to do is, and we'll talk about normal plane today, I think, but when you're doing friction problems, I remember this and from 1987, but I remember constantly finding unit vectors and taking something and finding a little mini vector, because that's how we had to rethink about how forces were reacting to planes, and that was something we were doing a lot of. We're not going to do a lot of application in this class. I'll leave that to physics, mainly because I think I'll mess it up, because I'm not a physics guy. I was going to say physician, but that's not it. Although I am neither that as well. Anyway, so make sure you know all of these. Today we're going to learn something that is super easy, The only thing hard about today is I'm going to show you where it comes from, but you don't need to know that. I just think it's interesting. And there was a time, this guy used to teach physics here. It was actually the father of the current physics teacher, Mr. Hope. His dad walked in my room one day and was like, hey, what's the dot product? And I was like, oh, the dot product. You know, when you do this and this, he goes, I know how to do it. What is it? I was like, I don't know. I had no idea what the dot product was. It was just this simple little process that we used to find angles between vectors and to do other things, but I didn't know what it was. So I started doing a little research, and I found out what this dot product was. Now, let me show you why I'm going to want to know dot product. Okay, first thing is, you're going to learn a couple things. And all this is in your formula sheet too, but we'll go over this today. So the dot product is this, what I'm about to show you. And by the way, don't confuse dot product with multiplication. A dot product, I'm going to use a dot. And I know we use a dot for multiplication. But there's also something called a cross product. We also use x's for multiplication. So with vectors, they're going to be dot products and cross products. So don't go, oh, I'm just multiplying those two. No. Okay? So dot product, if I had two vectors, like let's say that was called u vector u1, how about ux, uy, dot, and then say we had vx, vy. So just any random two vectors. To dot them, all I have to do is to multiply the x components, multiply the y components, and add them together. And when you do that, you come up with a single number. And that single number in and of itself does not mean much. But I'm going to show you kind of what it's going to take the place of. It is an incredibly useful piece of information that I don't know who discovered what I'm about to show you today, but that's all you have to do. So if I were to give you, for example, this vector, -2, 3, times, or not, sorry, times, dot 4, 7, the dot product says multiply the -2, multiply the -2 and the 4, multiply the 3 and the 7, add them together. And you get -8 and 21, which is 13. And that's your dot product. Okay? Now, how do I use that dot product? I'm going to show you so you know where we're heading, and it's going to kind of maybe go, there'll be like an aha moment. When I show you, you're like, oh, that makes sense. I'm going to use this with this formula to determine the angle between two vectors. Now, that means if I have any two vectors, I can find the angle between them using this formula. Now, I have people all the time that go, well, why do I need another formula for that? Why don't I just find that one's direction angle and that one's direction angle and then subtract them? Well, because sometimes you are going to subtract them. Sometimes you might, but you're going to have to actually visualize where they are to do that. With my formula, it's super quick. You don't have to think as much. You know, I mean, if they're right here, I might go, oh, big angle minus small angle. But what if one's positive and one's negative? You know, I mean, I guess technically you can still go big angle minus the negative angle. You can constantly do that kind of stuff, but depending where the vectors are, it gets to be a little confusing. Am I finding the small angle? Am I finding the big angle? So I try to avoid that mentality and use this formula. And here's your formula. To find that angle, I'm going to take the cosine of the angle, and I'm going to set that this formula, and I'm going to set it equal to, if say this was u and this was v, vectors u and v, or v and w, or whatever. I'm going to take the u vector, and I'm going to dot it with the v vector, and then I'm going to take the magnitude of the u vector times the magnitude of the v vector. So that would be the formula. So I would come in here and dot the u and the v like I just did here. Then I would come in here and I would take the magnitude of the u, and you already know how to do that, right? Say this was vector u. Like if that was vector u, you take the magnitude and you get root.
Yes.
What? For the magnitude?
13.
Root 13, right? That squared plus that squared, add them together, square root it. To get the magnitude of that, you get
65.
Root 65. And you plug the first root there, the second root there, you do the dot product, which we already did, which is 13. You plug the 13 in there, And to find the angle, what would you have to do then? Inverse cosine. So this is what it would look like. You'd have the dot product right here. If this was u right here, and if that was v. So if it was, you'd have the dot product there. You'd have the square root of, what did we say, 13 right there. You'd have the square root of 65 right there. And you would come in here and you would do inverse cosine of whatever that is. I usually type that in my calculator because I know that two roots multiplied together is just one big root. I would just put it all in one big radical. I'm not going to simplify, I'm not going to rationalize, I'm not going to do anything. I'm going to let my calculator do the work. And here's the beauty of this. Where is inverse cosine defined? 0 to 180? Any vector you draw on the planet, isn't there an angle that's between 0 and 180 that's between them? I mean, even if the angles look like this, you could say, well, that's bigger than 180. True, but that's not. So it'll always find the angle, and it can find the angle because it's defined between 0 and 180. So you never have to worry about adding 360 or adding 180 or doing anything like that. It'll always find the smaller of those two angles, which is good enough. That's the angle between them. Now, why does this work? Okay, that's what I wanted to show you. But ultimately, these are the main two topics out of today. You got to be able to use this to find the angle. Guess what the biggest mistake is when I say find the angle between the two vectors? Biggest mistake. People forget to inverse cosine. They just do this and type this in the calculator and they spit it out. You with me? Guess what the biggest mistake on dot product is? You'd think there'd be no mistakes on dot product. People pull out this formula. Now this has the dot product in it for sure, but this is not the dot product. This is just a formula to calculate the angle between two vectors, right? And there's another formula I think I put in your formula sheet, but I never use it. I mean, you can if you want, but I use this. All right, so let me show you where all this comes from, and you don't have to take notes on it. My goal, because I have it all in your notes, but here's what I really want you to be able to see. And I need to go back to one small thing that I mentioned yesterday but didn't talk a lot about. Do you remember me mentioning that there were... Do you remember me saying, what do you do if I wanted to say add two vectors together? That was pretty good. What could you do to add two vectors that you don't know their components, you just know their pictures? Yes? Okay, the parallelogram method, I'm not a huge fan of, but I've been taught that for years. But it is a method I want you to know. You can take that, and it actually is really good sometimes to use. So I'm not saying it's a bad thing, but like if I had the option, you could save a little bit of a step. The parallelogram method says, all right, remember, I've got to keep the magnitude, the length, and the direction angle the same. I could shift that over to here. So as long as I draw it in the same direction with the same length, it's an equivalent vector, right? So I shift it over there and connect the starting points. This would be the parallelogram method. Okay? So now it looks like this. So the parallelogram method says, all right, make a parallelogram out of this. So make a side parallel to that, and a side parallel to that, right? And then draw from there to the opposing diagonal, or draw an opposing diagonal. So this is basically vector V added to vector W. Are you with me on that? Now the other way to do it is instead of drawing them connected out of the same point, this is called head to tail or end to end, depending on who you talk to. The other method says, here I'll just redraw these. Let's just say this was vector V and say that is vector W. The other is take this and put it where the other one ends, make this begin. So I can put that here, again, same length, same direction. And then you just go from the beginning of the first one, since it's going here then there, to the end of the second one. And that could be my V plus W. But if you really think about it, it's kind of the same thing, right? I mean, when I put mine right here, I'm still drawing it right there. So that W there is the same as W being right there, and then beginning of the first to the end of the second. And people call that head to tail, end to end. Depends on who you talk to or what book you read. Are y'all with me? Now here's what I need you to understand. To add these two vectors, it's not doing this. I'm not taking U and then taking W and then calling that U plus W. That's not true, is it? It's the beginning of the first to the end of the second. So based on this, check this out. This is where your dot product comes from. So what if, ultimately, I was trying to get you to find the angle between two vectors? Okay? I don't know, maybe the vectors are V and W, whatever. And I'm trying to find this theta. And all you have is this and this. Now, would it make sense that if you didn't know anything about the formula that I just gave you, if I know these two vectors, I could find their lengths, couldn't I? Are you with me? And if I know these two vectors, I bet there's a way to find that vector also. And if I can find this vector also, I can find its length. And once I'm dealing with lengths, what am I dealing with now? Triangles. And how do I find an angle if I'm given triangles? Three sides. We're doing this, actually repeating this again next chapter. If I'm given three sides of a triangle, side, 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 what do I use to find an angle? Rhymes with pa of mosines. Law of cosines, excellent. Okay, so law of cosines, right? So I'm basically going to try to do law of cosines with this. Now here's where you got to be careful. How do I use the vectors to describe this? Now we just said that if I had this vector, and then I had another vector tacked onto the end of it, how would this vector look? This vector is a result of that vector and that vector being added together, isn't it? So isn't W plus U equal to V if V goes that way? Are you with me on that? So if I give you W and I give you V, which are these two, I would have to get a relationship between these three. So what I do is say W plus U equals V. I did it a different way here. I mean, it's okay, hold on. I went U, V plus U is W. We'll do it that way. V plus U, right? V, but I could do it the other way too. I'm just going to try to keep my notes. V plus U equals W. Does that make sense? Because I'm going beginning to end, beginning to end, beginning of the first to the end of the second. So V plus U is W, and if V plus U is W, and I'm looking for U, I can subtract the V. So this is how I would find the U vector. Are y'all seeing that? Now again, you're not going to have to do this, but I'm just showing you. So right here, I would take the W vector, which I know, and I would take the V vector, which I know, and how do you subtract two vectors? X minus X, Y minus Y components, and there is my new U vector. Now here's what I would do to make this fit my narrative in law of cosines. Now that I have vector W, vector V, and vector U, I would have to use law of cosines. And this is where the magic of the dot product happens. So check it out. If I have those three vectors, what I need to do is find their magnitudes and plug them into the law of cosines. You remember the law of cosines? It was like a squared equals b squared plus c squared minus 2bc cosine of the angle between. Y'all remember that? Yes? No? But I got to have lengths of the sides, right? Y'all in a coma? Y'all with me? Got to have lengths? Okay, so check it out. I need the lengths of all these. So how do I find the length? And that's why I have these magnitudes in there. Those are lengths. So the magnitude of the U, think about all this. I know I can find it, but let's just say I went ahead and found all those lengths. Now look what happens when I think about this. To find this angle theta, I'm going to go U squared, that side squared, equals that side squared plus that side squared minus 2 times that side, cosine of the angle between. That's law of cosines. It'd be the same thing as if I did this. if I called that angle A, and that was A, and that was B, and that was C, I'd say that squared plus that squared minus, I'm sorry, I'd say right here I would go A squared equals that squared and that squared minus 2BC cosine of the angle between. That's what I'm doing here. Okay? Now check it out. If that's true, let's solve for cosine theta. Now cosine theta says, first subtract the W squared and the V squared. I'm going to subtract that over. Are you with me? Then I'm going to divide by that. I'm going to put that, first I divided by -2, okay? Now, I want you to see something right here, okay? And this is what's going to hopefully kind of all come together and make you go, ah. Watch the math of this. Notice I did not get rid of the W and the V yet. Magnitude. So I'm going to divide by the -2. Now look at this. The magnitude of U, if you're looking at your notes and following this, you'll see that. If I square it, what does the square do to the magnitude? Remember, each magnitude has a square root over it, right? So what does the square do to the magnitude? You guys stay with me. I think y'all are really in comments. Right here. Here's U, right here. What would a squaring that do to the magnitude? Get rid of the square root, right? So if I square any of these, which I'm doing right now, if I square any of the magnitudes, it's getting rid of the square root, right? So come back down to my formula. So first one, here's the big, ugly magnitude of U. If I square that whole thing, the square root goes away and I'm left with this. If I square the W, it makes that square root go away. If I square the magnitude of the V, it makes that square root go away, doesn't it? And now that all the square roots have gone away, and again, remember I've kept those magnitudes over there, I want you to see something. I'm going to FOIL that out. I'm going to FOIL that out. I'm going to not FOIL that because it's not being squared, but I'm going to distribute the negatives. And I get to here, and then a bunch of junk cancels, and I'm left with this. And then the -2 cancels, and I'm left with this. Huh. What is WX VX plus WY VY? That's my dot product. Which means I don't have to do any of this crap. All I have to do, if I'm given vector V and vector W, if I'm given these two vectors, all I have to do to find the angle is to do the dot product of them. Take the W x coordinate and the V x coordinate and multiply them. Take the WY coordinate and the VY coordinate, multiply them and add them together. So that whole thing that we did, all of this, which we've been simplifying all the way down, all of that because it's simplifying to something really nice, somebody just came up and said, man, if it's that simple, turns out I don't even have to find the other side of the vector. I never had to find U, did I? Looked like I needed to, but in the end, all that was left was W and V stuff. So the beautiful part about this is you don't have to worry about this third side anymore. If I want to find the angle between the two vectors, I can jump straight down to my formula and just use the dot product right there in its place. And that's where this formula comes from. You got tracking with me? Now, some of you don't care about proof, but if you ever are wondering where in the world the dot product came from, the dot product was essentially what? What part? It was part of the law of cosines, wasn't it? The dot product was me simplifying all this part of the law of cosines where I kept the a squared minus b squared c squared and divided by the -2. All of that, that's my dot product. It's just unsimplified here. But that sure is a huge thing now for you because you don't even need the law of cosines. You can just use that formula to find the angle between any two vectors. I think that's pretty big deal. But anyway, so that's where this comes from. And your job is basically to know those things. So that's for a different day. So real quickly, a couple little rules for dot products. And most of these seem pretty obvious. But what do you think U dot V and V dot U's relationship are if I'm dot product two vectors? If I switch the order, should that change the value? Because I'm still multiplying x's and y's and adding them together, right? So these are equal. What if I had a 0 times a vector? What do you think happens when you have a 0 times a vector? You don't get 0. You get what?
The 0 vector.
The 0 vector. Are you with me? That's a big deal, actually. Because if I have a vector like 2, 3, and I multiply it by a scalar, I'm getting the 0 vector, not the number 0. And again, the 0 vector is kind of an odd commodity, but whatever. Anybody have any idea what you might do if I have a vector dotted with the sum of another vector? Now, obviously, I can add these together and get a vector, and then multiply it, but do you think I have any other options? Take a guess. I can distribute it in. So, yes, I can definitely add vectors, because you know how to do that. But another option would be to distribute that in, and then you'd have u what? Dot v plus u dot w. And remember, dot product doesn't mean multiply, it means you use that dot product. Anybody have an idea about this one? What happens when you dot a product with itself? Let me give you an example. 2, 3, dot with 2, 3. What do you end up getting? 2 squared plus 3 squared? You with me? Doesn't that kind of look a little like magnitude? Kind of looks like magnitude squared. So that is another way of saying the magnitude of v squared, or basically the magnitude without the square root. Trying to see if I have anything else. It's really important. Oh yes, I got 2 minutes. Okay, last thing I want to talk about. What if I gave you these 2 vectors? How about this? If I asked you what was the angle between them, what could you do? Angle between the 2 vectors. Don't be shocked. I've literally spent half the day talking about it. What would you do? You do the whole cosine of the angle equals the dot product over the product of the magnitudes, and then you inverse cosine finds your angle, right? Now I have a question. If these kind of have the same slopes, over 1, down -2, over 4, down -8, if they have kind of the same proportions, then aren't they moving in the same direction? We call that scalar multiples, which means if I factored a 4 out of this, what would I have? The same core vector. Well, a way to check to see if they're going in the same direction, or what we would call parallel, is to do this. Instead of thinking scalar multiple, just take that, put it on top of this or underneath it, and look at the fractions. If your values of the 2 fractions are equal, 4 over 1 equals -2, they're parallel. And as you're walking out the door, and you'll see this tonight, if the dot product is 0, they're perpendicular. Most of the time, but I'll get into that tomorrow.